Today we study ESA20H, completing the square and differential equation. An arbitrary quadratic equation for x with real coefficients a, b, c can be expressed as where constant a is not 0. We can show that this equation, can be reduced into this form that can be factorized. Once it is possible, then we can simply find the solution for x like that. We do this just like what we did in middle school. Because a is not 0, we can divide this equation by a. Then x squared b over ax c over a equals 0. By completing the square, this one can be reproduced by a square. I missed the square in here. X plus b over 2a squared subtracted by this constant term squared subtracted. And c over a is in here. Again, I have missed power 2 in this expression. Now, this one can be expressed in this manner. B squared minus 4ac over 4a squared. Again, I have missed power of 2. Now, this one is a factorizable. A squared plus minus b squared equals a plus b, a minus b equals 0. So that means a plus b equals 0 or a minus b equals 0. That means a equals plus minus b, something like that. As a result, we have found the solution for the quadratic equation is minus b plus minus square root b squared minus 4ac over 2a. Now we can make use of these relations we learned in middle school to solve the equation of motion for a damped harmonic oscillator. A damped harmonic oscillator is F equals ma, and ma, that is the force. Force is the sum of the two contributions. Minus kx is the spring's restoring force, and this minus bx dot, that is opposite to the velocity, that is called the damping force. We call this b as a damping coefficient, and k is the spring constant. We'd like to solve the corresponding quadratic equation in which x double dot is replaced with x squared, x dot is replaced with x, and x is replaced with 1. Then the quadratic equation, we know how to solve this quadratic equation. That is just copy of this formula. A, B, C. We substitute M for A. B is to be the same. K for the C. In here. So after the replacements, we find that the solution for x in this corresponding quadratic equation is minus b over 2m plus minus, I have replaced the sign inside the square root. This b squared is a plus b squared in here, but it is now minus b squared. Therefore, I have to consider I. where we have made use of the identities. Square root of minus p is square root of minus 1, square root of p, and square root of minus p minus 1 is the pure imaginary number I. Now we recall this. X of t is exponential of minus b over 2mt multiplied by y of t. We can take the first order derivative and second order derivative by making use of the Leibniz rule of the product function. What's that? This is the first order time derivative of the product a, b. This is the second order time derivative of the product a, b. So I have a dot b plus a b dot. And this one, we have a double dot a b plus e 2 times a dot b dot plus a b double dot. So we substitute exponential minus b over 2m t for a, the y for b in these identities. Finally, we know that a dot b over 2m exponential minus b over 2m t, a double dot, this one appears twice, and the single dot appears once, but I have to multiply the multiplicity factor 2 to find the expression like that. As a result, if I substitute these expressions for those x in the equation of motion for the damped harmonic oscillator, we finally obtain the expression. This first order derivative term cancels exactly, and what we find is the exponential something and this. The equation of motion for the damped harmonic oscillator is 0, and exponential x can never cross the x-axis. So it is a positive definite in any case for any x. And it is true for any complex number. It never touches 0. As a result, equals 0 is equivalent to the equals 0 for the y's equation. We recall this y double dot plus y equals 0, y double dot minus y equals 0, whatever alpha, whatever positive alpha is, maybe, that we know how to solve these 3 kinds of trivial second-order linear differential equation. As a result, completing the square is very, very useful to simplify the equation of motion of the second-order differential equation, especially for the damped harmonic oscillator. That's it for today. Thank you.